Right now, you are sitting somewhere. Maybe it is a room you know well, a chair that fits the shape of your body from years of use, walls that have held their position for as long as you have lived in this space, a ceiling that does not move, a floor that does not shift. The light coming through the window behaves exactly as it always has, bending around the same corners, settling on the same surfaces, fading at the same hour. Everything around you is operating according to rules that have never once failed you, not in the way that matters, not in the way you can feel. You have spent your entire life inside a set of physical laws that have never broken. You have dropped objects and they have fallen. You have pushed against walls and the walls have pushed back. You have watched the sun rise and set with a regularity so perfect that ancient civilizations built entire religions around it. The universe, in every moment of your direct experience, has behaved like something you can trust completely, like something solid, like something real. Now hold that feeling carefully, because what follows is going to ask you to examine it. 73% of everything that exists is invisible. It cannot be seen, touched, collected, or detected by any instrument humanity has ever built. It does not interact with light. It does not cluster around galaxies. It does not behave like any known particle or field in the standard model of physics. And yet, it is the dominant component of the universe. It outweighs everything you can see, everything you can measure, and everything that has ever constituted the subject of human scientific inquiry by a ratio that makes ordinary matter look like an afterthought. We call it dark energy. We gave it a name because naming things creates the impression of understanding. Scientists are as susceptible to this as anyone. You name something and it feels contained, classified, domesticated. But dark energy is none of those things. It is a placeholder for ignorance dressed in technical language. What it actually refers to is a pressure, a repulsive force embedded in the fabric of space itself that is causing the universe to expand, not just steadily, but with increasing acceleration. The galaxies are not merely moving apart. They are moving apart faster than they were yesterday and slower than they will be tomorrow. The universe is not drifting. It is accelerating toward a state that has a name in cosmology, a name that implies cold, darkness, and absolute isolation at a scale that makes the current universe seem intimate. For decades, physicists have known this and have lived with the discomfort of not being able to explain it. The calculation of what dark energy should be, derived from the most precise and successful physical theory in human history, quantum field theory, produces a number that is not merely wrong. It is wrong by a factor of 10 raised to the power of 120. This is not a rounding error. This is not a problem of measurement precision. This is a conceptual catastrophe so severe that physicists gave it a name, the cosmological constant problem, and it has remained unsolved for the better part of a century, until now. What CERN has begun to extract from the data of its Large Hadron Collider, from the precise measurement of particles that exist for fractions of a second before dissolving back into the quantum foam, is not a reassuring resolution. It is not the kind of answer that makes the problem smaller. It is the kind of answer that makes the problem clearer. And clarity, when the problem is this one, is its own form of dread. The data suggests that the vacuum of space, the baseline condition of reality, the nothing from which all somethings emerge, is not in its lowest possible energy state. It is sitting in a temporary configuration, a local minimum, a valley that appears stable from the inside, but is not, by the strict mathematics of quantum field theory, the deepest valley available. Somewhere beyond where we sit, past an energy barrier that quantum mechanics does not treat as impassable, there may be a lower state. And if the vacuum ever finds its way there, everything that is possible in our current configuration of physical law, every particle, every force, every atom, every arrangement of matter that has ever lived or thought or wondered, ceases to be possible. This video is not speculation. Every concept you will encounter here is grounded in established physics, peer-reviewed research, and theoretical frameworks that the scientific community takes with complete seriousness. The discomfort you will feel is not manufactured by dramatic language or exaggerated claims. It is the natural response of a mind encountering what the evidence actually says. The question at the center of this video is not complicated. It can be stated in a single sentence. What if the ground beneath reality is not permanent, and we have just found the first real evidence that it is slowly giving way? We are going to follow that question all the way down. Every step will be grounded. Every implication will be earned. And at the end, there will be no resolution, because the physics does not offer one. Begin. The silence before the number. There is a number at the center of this story, and before you can understand why it matters, you need to understand the silence that surrounded it for most of human history. For millennia, the cosmos appeared to be something fixed, not just stable in the ordinary sense, but ontologically permanent, as if the universe were a category of existence that sat above change rather than within it. Ancient astronomers mapped the sky as a ceiling. The stars moved in their cycles, but the cycles themselves never changed. The geometry of the heavens was eternal. The laws that governed the motion of objects on Earth were believed to be the same laws that had always governed them, and would always govern them, without beginning or end. This was not naivety. It was the reasonable conclusion of careful observation over long timescales. Nothing in the available data suggested that the universe had a history in the sense of having been different in the past and heading toward being different in the future. The universe, to every civilization that ever looked up at it, was the permanent background against which temporary things like people and civilizations and stars played out their brief episodes. Even Isaac Newton, who revolutionized the understanding of physical law more completely than anyone before him, did not question the fundamental stability of the cosmos. His equations describe the motion of planets and falling objects with an accuracy that had never been approached. But they described motion within a fixed stage. Space, for Newton, was absolute, eternal, an infinite and unchanging container. Time moved through it at a constant rate. The laws that governed everything within it were the same everywhere and at every moment. The universe was not a thing that had properties or a history. It was the context in which things with properties and histories existed. This picture held for more than 2 centuries. It was not overturned gradually. It was dismantled within a single generation by a single person that with a set of equations that took a decade to fully comprehend, in 1905, Albert Einstein published the special theory of relativity. In 1915, he completed the general theory. What general relativity described was not motion within a fixed space. It describes space itself as a dynamic entity, something that could curve in the presence of mass, something that could stretch and compress, something that responded to the distribution of matter and energy within it. Space was not a container. It was a participant. And a participant can change. Einstein himself did not initially follow this conclusion where it led. When he wrote down his field equations and realized that they predicted a dynamic universe, one that would either expand or contract depending on its contents, he was troubled. A dynamic universe implied a beginning. A beginning implied questions that physics could not yet answer. And so he did something that would later haunt him. He inserted a term into his own equations, an additional constant, which he called the cosmological constant, denoted by the Greek letter lambda. This term acted as a repulsive pressure that exactly balanced the gravitational attraction of matter, holding the universe in a steady state. It had no physical motivation beyond the desire to preserve stability. It was, in his own later description, inserted by hand. The universe did not cooperate with his preference. In 1929, Edwin Hubble's observations confirmed that the galaxies were receding. The universe was expanding. There was no need for a stabilizing constant. Einstein withdrew it, reportedly calling it his greatest blunder. The cosmological constant was removed from the equations and set to zero. Physics moved on. But setting a constant to zero is not the same as explaining why it is zero. And the question of why the energy of the vacuum, which the cosmological constant was eventually understood to represent, should be zero rather than some other value, was a question that physics had not answered. It had simply decided not to ask it. That decision held for 60 years. Then two teams of astronomers pointed their telescopes at distant supernovae, measured the rate of cosmic expansion at different points in history, and found something that forced the question back to the center of physics with an intensity it has never since lost. The cosmological constant was not zero. It had never been zero. It was small, the almost impossibly small by the standards of quantum theory, but it was not zero. And its presence in the equations meant something that neither Einstein nor anyone in his era had been prepared to face. The vacuum of space has energy, real, measurable, consequential energy, and nobody knows where it comes from, why it has the value it has, or whether that value is permanent. That is the number at the center of this story, not the value itself, which is approximately 1.1 times 10 to the negative 52 joules per cubic meter, but the silence around it, the silence of a century of physics that knew the question existed and chose, for reasons of mathematical convenience, to pretend the answer was zero. The silence is ending now, and what is replacing it is not reassuring. What Edwin Hubble saw and what it cost us. In the early 1920s, the dominant view among astronomers was that the Milky Way was the entire universe. The spiral and elliptical nebulae, visible through large telescopes, were assumed to be clouds of gas within our own galaxy, formations of dust and plasma lit by nearby stars, features of the local landscape, rather than distant objects of comparable scale to everything we knew. The universe, on this view, was bounded. finite, comprehensible in principle, even if vast in practice. It had edges, even if we could not see them. It had a shape, even if we could not trace it. It was, above all, something that could in theory be described completely, a closed system with a finite inventory. Edwin Hubble, working with the 100-inch Hooker telescope at Mount Wilson Observatory in California, began to dismantle this picture in 1923, using a class of variable stars called Cepheids, whose intrinsic brightness varies in a regular and predictable cycle. He was able to measure the distance to the Andromeda Nebula with a precision that had not previously been possible. The result was unambiguous. Andromeda was not a cloud within our galaxy. It was a galaxy in its own right, located at a distance of approximately 2.5 million light-years from Earth. The universe was not the Milky Way. The Milky Way was one structure among an unknown but clearly enormous number of similar structures, each containing hundreds of billions of stars, distributed across a space that made all previous conceptions of the cosmos look parochial. This was already one of the most significant discoveries in the history of science, but it was not what Hubble is most remembered for. Then over the following years, Hubble systematically measured the distances to dozens of galaxies and compared those distances to another quantity, the redshift of light arriving from each galaxy. Redshift is a stretching of light wavelengths toward the red end of the spectrum, and it is caused by motion away from the observer, in the same way that the sound of a moving vehicle drops in pitch as it travels away. The greater the redshift, the faster the recession. What Hubble found when he compared redshift to distance was a relationship so clean and so consistent that it amounted to a law. The further a galaxy was from Earth, the faster it was moving away. Not slightly faster, proportionally faster. Double the distance, double the recession speed. The immediate implication was that the universe was expanding. But the deeper implication took years to absorb fully. The galaxies were not moving through space. Space itself was expanding, carrying the galaxies within it like marks on the surface of an inflating balloon. There was no center to the expansion and no edge. Every point in space was moving away from every other point. The expansion was not a feature of the local environment. It was a property of the universe as a whole. And if the universe was expanding now, it had been smaller in the past. Trace the expansion backward, and you arrive at a moment of extreme density and temperature, a beginning that physics could describe with increasing accuracy as the mathematics of general relativity were applied at smaller and smaller scales. The universe had a history. It had an origin. It was not eternal. It was a process. This was the cost of Hubble's discovery. The stable, eternal, comprehensible cosmos was replaced by something dynamic, evolving, and finite in time, if not necessarily in space. The universe had been born, and if it had been born, it might also, in some sense, die. The question of what the expansion would do over time, whether gravity would eventually slow and reverse it into collapse, whether it would continue indefinitely at a decreasing rate, became one of the central questions of 20th century cosmology. For 70 years, physicists assumed the answer was one of those two options: expansion slowing down due to gravity, leading eventually to a big crunch, or expansion continuing forever but decelerating as the density of matter thinned. The possibility that the expansion might be accelerating, then driven by some energy source not accounted for in any existing model, was not taken seriously as a prediction. It was not expected. It was not looked for. When it was found, it arrived the way the most disturbing discoveries always do, not with fanfare, but with data that simply refused to fit the expected pattern. The two teams that found it in 1998, the High Z Supernova Search Team and the Supernova Cosmology Project, were not looking for dark energy. They were measuring type 1, a supernovae, at various distances as standard candles, objects of known intrinsic brightness that can be used to determine precise distances across cosmological scales. They expected to find that the expansion was slowing. They found the opposite. The distant supernovae were fainter than they should have been for a decelerating universe. They were further away than expected. The expansion was not slowing, it was speeding up. Something was pushing space apart. Something with energy, with pressure, with effects measurable at the largest scales we can observe. Something that did not fit into any existing category of matter or radiation. The word that was eventually settled on, dark energy, was a deliberate echo of dark matter, another mysterious component of the universe, whose existence had been inferred, but whose nature remained unknown. The naming was an acknowledgement of ignorance. We did not know what it was. We only knew what it was doing, and what it was doing was rewriting the future of the universe in terms that were far stranger than the ones physicists had been working with. The cosmological constant returns from the dead. Einstein removed his cosmological constant from his equations in 1931, 2 years after Hubble's observations made the case for an expanding universe impossible to dismiss. The removal was not just a correction to his model, it was an expression of a philosophical commitment. Einstein believed that the fundamental equations of physics should contain only what is necessary, that every term in an equation should correspond to something real, and that inserting a constant purely to obtain a desired result was a kind of intellectual dishonesty. The cosmological constant, in his view, had served a purpose that turned out to be wrong. He had wanted a static universe. The universe was not static. The constant was therefore a mistake, not just in its value, but in its motivation. He withdrew it and hoped it would not be needed again. For 67 years, it was not needed. The physics of an expanding universe could be described to sufficient accuracy without it. The question of how the expansion would evolve over time was treated as a question about the density of matter and radiation in the universe. If the density was above a certain critical threshold, gravity would eventually halt the expansion and reverse it. If it was below, the universe would expand forever, but at a decelerating rate. Either way, no additional term was required. The cosmological constant was a historical footnote, an example of a great scientist making a correctable error, and the field moved on. What it moved on without noticing was that setting the cosmological constant to 0 is not a neutral act. A constant set to 0 is still a constant. It is a specific value. And assigning it that value requires justification in the same way that assigning it any other value would. The question of why the vacuum energy of space should be exactly 0, not approximately 0, not negligibly small, but precisely and permanently 0, was not answered by setting it to 0. It was assumed. The assumption was convenient. It was productive. It allowed cosmology to develop through most of the 20th century without confronting a problem that had no available solution. But it was not justified by any physical argument. It was a choice made for the sake of simplicity, dressed up by the passage of time as settled a fact. Then the supernovae data arrived in 1998, and the cosmological constant came back. It came back not as Einstein had conceived it, in the stabilizing term, inserted to prevent unwanted dynamics, but as something far more fundamental, the energy density of the vacuum itself. The discovery that the expansion was accelerating implied that empty space was not truly empty. It had energy, and that energy had pressure, a negative pressure that acted repulsively over large scales, driving space apart rather than drawing it together. The mathematical description of this behavior was precisely Einstein's cosmological constant, with a positive value, reinstated as a real physical quantity rather than a mathematical convenience. The immediate response of the physics community was not celebration. It was something closer to alarm, that because reinstating the cosmological constant as a real physical quantity meant confronting the question that had been avoided since the development of quantum field theory. Why does the vacuum have the energy it has, and not some other energy? Quantum field theory predicts that the vacuum should be seething with energy. Every quantum field that exists contributes a 0-point energy, a minimum energy that the field retains even in its lowest state due to the uncertainty principle. The sum of all these contributions across all known fields produces an enormous number. By the standards of quantum theory, the number is natural, meaning it does not require fine-tuning to obtain. It is simply what you get when you add up the contributions of all the fields. And when you compare this number to the observed value of the cosmological constant, you find a discrepancy of 10 to the power of 120. The observed value is not close to the predicted value in any sense that physicists would normally consider meaningful. It is not within an order of magnitude. It is not within 10 orders of magnitude. It is 120 orders of magnitude smaller than the prediction. The vacuum energy that quantum field theory demands would produce a universe so dense with energy that it would expand to its current size in a Planck time, approximately 10 to the negative 44 seconds, and continue expanding at a rate that would tear every structure apart before the first particle interaction could occur. We would not be here. Nothing would be here. And yet we are. And the vacuum energy is not the predicted value, but something vastly, impossibly smaller. The cosmological constant has returned. But returning has only made the problem deeper. The worst prediction in the history of science. There is a phrase that physicists use, not casually, to describe the cosmological constant problem. They call it the worst prediction in the history of science. This is not hyperbole designed to make a lecture more engaging. It is an accurate description of the quantitative failure involved, and understanding why requires sitting with the number itself for long enough to feel its weight. The prediction comes from quantum field theory, which is, in every other context, the most successful physical theory ever developed. Its predictions of quantities, like the anomalous magnetic moment of the electron, agree with experimental measurements to more than 10 decimal places, No other theory in any field of human inquiry has achieved this level of precision. The standard model of particle physics, built on the foundations of quantum field theory, has predicted the existence of particles before they were discovered, described their properties with extraordinary accuracy, and withstood decades of experimental challenges without breaking. If you are inclined to trust any scientific framework, quantum field theory has earned that trust more than any other. And this framework predicts that the vacuum of space should contain approximately 10 to the power of 113 joules of energy per cubic meter. The observed value is approximately 10 to the power of -9 joules per cubic meter. The ratio between these two numbers is 10 to the power of 122. This is the discrepancy. This is the failure. To develop an intuition for the scale of this failure, consider some comparisons. The observable universe is approximately 93 billion light-years in diameter. A proton is approximately 10 to the -15 meters in diameter. The ratio between the size of the observable universe and the size of a proton is roughly 10 to the power of 41. The ratio between the predicted and observed vacuum energies is 10 to the power of 122. This means the mismatch between the prediction and the observation is vastly larger than the ratio between the largest and smallest objects we can meaningfully discuss in physics. It is not a small discrepancy. It is a discrepancy that dwarfs every other scale in science. And yet quantum field theory is not wrong. Its predictions in every other domain are verified. So either there is some mechanism that cancels out almost all of the vacuum energy, leaving only the tiny remnant we observe, or there is something fundamentally incomplete about our understanding of how quantum field theory and gravity are related. The first option requires a cancellation of almost unimaginable precision. Imagine two numbers, each with 122 digits, that cancel each other to 120 decimal places, leaving only the last two digits as the result. This is the degree of fine-tuning that would be required. It is not impossible, but it is deeply, philosophically unsatisfying, because there is no known mechanism in physics that would produce this cancellation naturally. It would have to be arranged. And arranged by what, or by whom, or for what reason, are questions that physics cannot answer. The second option, that the relationship between quantum mechanics and gravity is not what we think it is more theoretically attractive. It suggests that the resolution lies in a theory of quantum gravity, a framework that describes both the quantum behavior of matter and the geometric behavior of space-time within a single, consistent mathematical structure. String theory is the most developed candidate for such a framework. Loop quantum gravity is another. Neither has yet produced a clear resolution of the cosmological constant problem, though both offer partial perspectives that physicists continue to develop. What makes the situation more uncomfortable, not less, is that the discovery of dark energy in 1998 did not resolve the cosmological constant problem. It refined it. Before 1998, Dumna could at least entertain the possibility that the vacuum energy was zero, and that some undiscovered symmetry was responsible for its cancellation. Zero is a special number. it can be the result of an exact symmetry, a cancellation that is absolute rather than approximate. After 1998, that possibility was eliminated. The vacuum energy is not zero. It is small, but it is not zero. And a number that is small, but not zero, is far harder to explain than a number that is exactly zero. Exact zeros can be protected by symmetry, small numbers cannot. They require fine-tuning, or they require an explanation, and no explanation exists. The worst prediction in the history of science was made by the best predictive framework in the history of science. That combination, failure by the most reliable tool available, is not an anomaly to be explained away. It is a signal that something fundamental is missing. And CERN's recent measurements are beginning to narrow down what that missing thing might be in a direction that offers no comfort. What empty space actually is. Take a moment to imagine empty space, a perfect vacuum, a region of space from which every particle has been removed, every photon evacuated, every atom drawn away until nothing remains. This is the mental image most people carry of the word vacuum. Absence, blankness, a region of pure nothing that serves as the background against which the objects of the world are arranged. In everyday experience, this intuition is serviceable. In physics, it is wrong in a way that has consequences reaching to the edge of the cosmos. Empty space, according to quantum field theory, is not empty. It is never empty. It cannot be empty. The uncertainty principle, which governs the behavior of quantum systems at the smallest scales, forbids the simultaneous specification of certain pairs of physical quantities, including the energy of a region of space and the time over which that energy is measured. This means that even in a region of space containing no particles, the energy cannot be precisely zero at all times. It fluctuates constantly, without pause. The vacuum of space is a churning, dynamic medium of quantum fluctuations, where energy borrowed from the uncertainty principle spontaneously creates pairs of virtual particles that annihilate each other in timescales so brief they exist at the edge of what is physically meaningful. These are not imaginary objects, introduced to make the mathematics work. Their effects are measurable. The Casimir effect is one of the most direct demonstrations. If you take two uncharged metal plates and place them very close together in an otherwise empty region of space, the quantum fluctuations between the plates are restricted to wavelengths short enough to fit between them, while the fluctuations outside the plates can take any wavelength. This difference in fluctuation density creates a pressure imbalance that pushes the plates together. The force has been measured with precision instruments and matches the theoretical prediction with extraordinary accuracy. The vacuum pushed the plates. Something that is supposed to contain nothing exerted a measurable force. The Lamb shift provides another confirmation. When physicists measure the energy levels of the hydrogen atom with sufficient precision, they find that two energy levels that should, according to simpler quantum mechanics, be exactly equal, are in fact slightly different. The difference, called the Lamb shift, after Willis Lamb, who first measured it in 1947, arises because the electron interacts with the virtual particles in the vacuum around it. The vacuum fluctuations perturb the electron's energy in a calculable way. The calculation agrees with measurement to many decimal places. The vacuum is interacting with matter. It has physical consequences. It is not nothing, The anomalous magnetic moment of the electron offers a third, extraordinarily precise confirmation. The magnetic moment of the electron, a measure of how it interacts with magnetic fields, has been calculated in quantum electrodynamics, the quantum theory of the electromagnetic force. By accounting for the electron's interactions with the virtual photons and other virtual particles that constitute the vacuum fluctuations around it. The result agrees with the experimental measurement to 11 decimal places. This is the most precisely verified prediction in all of physics, and it depends fundamentally on the existence of vacuum fluctuations, on the reality of a vacuum that is not empty. So when physicists say that the vacuum has energy, they are not speaking metaphorically, they are describing a physical medium with measurable properties. This medium is the same everywhere in the universe. It is the lowest energy state accessible to physical systems. It is the background condition of reality. Everything that exists, every particle, every force, every field, exists as an excitation above this background. And the energy of this background, summed over all the quantum fields that exist, produces the number that quantum field theory predicts for the cosmological constant. A number that is 120 orders of magnitude larger than what we observe. The vacuum is real, its energy is real. The discrepancy between what it should be and what it is the deepest and most unresolved problem in theoretical physics. And it is not an abstract mathematical puzzle. It is a statement about the fundamental nature of the medium in which all of physical reality is embedded. The ground of everything is not what it appears to be. It is not stable in the simple sense. It is not passive. It is active, energetic, and structured. And the question of whether its structure is permanent or temporary is the question that CERN's measurements are now beginning, for the first time, to approach with something like a real answer. The Large Hadron Collider and what it was really searching for, beneath the border between France and Switzerland, in a circular tunnel 27 kilometers in circumference and approximately 100 meters underground, protons are accelerated to 99.9999991% of the speed of light and then collided with each other at energies of up to 13.6 tera-electron volts. The collisions last for fractions of a second. The debris they produce, the showers of secondary particles that spray outward from the collision point, are captured by detectors the size of cathedrals, instruments built from hundreds of millions of components, assembled by thousands of physicists over decades, capable of recording the position and energy of thousands of particles simultaneously in the microseconds following each collision. Most people know what CERN's Large Hadron Collider found. In July 2012, after decades of theoretical prediction and years of searching, the Higgs boson was observed for the first time. The announcement was greeted with genuine emotion. Press conferences at which physicists who had spent careers on the search were visibly moved. Peter Higgs, who had proposed the existence of the particle in 1964, was in the room. The discovery completed the standard model of particle physics, confirming the existence of the final predicted particle in the theoretical framework that describes the fundamental constituents of matter and the forces between them. It was described as the discovery of the century. It was given a Nobel Prize within the year. But there is a dimension of that discovery that received far less attention in the public celebration. A dimension that the physicists in that room understood immediately, and which has shaped the direction of theoretical physics ever since. The Higgs boson is not merely a particle. It is evidence of the Higgs field, a scalar field that permeates all of space and gives particles their mass through their interaction with it. And the Higgs field is not just a feature of the Standard Model. It is the key to understanding the stability of the vacuum. Here is why. Every quantum field has a potential energy, a value that depends on the configuration of the field. For most fields, the lowest energy configuration is the field value 0, and the field settles to this value in empty space. The Higgs field is different. Its potential energy is not minimized at 0. It has a shape that physicists describe as a Mexican hat, a potential that is higher at the center, where the field value is 0, and lower at a ring around the center, where the field takes a non-zero value. The lowest energy state of the Higgs field is not 0. It is a specific non-zero value, approximately 246 giga-electron volts, which we call the vacuum expectation value. Every particle that interacts with the Higgs field acquires a mass proportional to the strength of that interaction. This is the Higgs mechanism. It is the reason particles have mass. And the mass of the Higgs boson itself, the ripple in the Higgs field, is a measure of the curvature of this potential at its minimum. When CERN measured the Higgs boson mass at 125.25 giga-electron volts, they were measuring the curvature of the Higgs potential at its lowest accessible point, and this measurement, combined with the mass of the top quark, the heaviest known fundamental particle, determines something that goes far beyond particle physics. It determines the shape of the Higgs potential at much higher field values, values far beyond what the LHC can directly probe, values that correspond to the energy scales of the very early universe and the ultimate fate of the vacuum. What the measurement reveals, when the renormalization group equations are used to extrapolate the behavior of the Higgs self-coupling to higher energies, is that the curvature of the Higgs potential does not remain positive as the field value increases. At very high energies, the curvature turns negative. The potential, instead of continuing to rise, that begins to fall again. This means there may be a deeper minimum in the Higgs potential, far from the one we inhabit, a true ground state to which our current vacuum is not the bottom, but only a rest stop. The LHC was built to find the Higgs boson. It found it, and in finding it, it handed physics the most unsettling implication in its history: the possibility that we are not living in the ground state of reality, but in a temporary configuration that quantum mechanics does not forbid from changing. The Higgs field is not where it should be. You are familiar with the concept of stability, even if you have never formalized it. An object resting at the bottom of a bowl is stable. If you push it slightly in any direction, gravity pulls it back. The bottom of the bowl is a stable equilibrium. An object balanced on top of a hill is unstable. The slightest push sends it rolling irreversibly down the slope, never to return. These two situations, stable equilibrium and unstable equilibrium, are distinguishable by the shape of the potential energy surface in the vicinity of the object's position. The Higgs field occupies a point in a potential energy landscape. That landscape, called the Higgs potential, is a function that assigns an energy value to every possible value of the Higgs field. The vacuum state we inhabit corresponds to the field taking its vacuum expectation value, approximately 246 gigaelectronvolts. At this point, the potential has a local minimum. The field, if perturbed slightly, returns to this value. By the ordinary definition of stability, this is a stable configuration. But stability has two versions. Absolute stability means that the equilibrium is the lowest possible energy state, that there is no lower valley anywhere in the landscape. Metastability means that the equilibrium is a local minimum, a valley, but not the global minimum. There is a lower valley somewhere, separated from the current position by an energy barrier. The object in the local valley is stable against small perturbations, because those perturbations do not provide enough energy to climb over the barrier. But it is not stable against quantum tunneling, which does not require climbing over the barrier but can pass through it. The question of whether our vacuum is absolutely stable or merely metastable depends on the shape of the Higgs potential at field values, far above the vacuum expectation value. This shape cannot be measured directly because the energies involved are beyond the reach of any current accelerator, but it can be calculated using the renormalization group equations that describe how physical parameters change with energy scale. These equations take the measured low energy values of physical constants, including the Higgs mass and the top quark mass, and evolve them mathematically to higher energies. When this calculation is performed with the values measured at CERN, the result is that the Higgs self-coupling constant, which controls the curvature of the potential, runs towards zero and then turns negative at an energy scale of approximately 10 to the power of 10 or 11 gigaelectronvolts. A negative self-coupling means the potential is no longer bowl-shaped at that field value. It begins to slope downward. The implication is that the Higgs potential has a second minimum, deeper than the one we occupy, at the field value far above the vacuum expectation value. If this is correct, the vacuum we inhabit is metastable. It is not the lowest energy state. It is a local minimum, separated from the true ground state by an energy barrier. Quantum mechanics does not treat barriers as absolute obstacles. Given sufficient time, quantum tunneling allows a system to pass through a barrier it could not classically overcome. In the context of the Higgs field, this means that a small region of space could spontaneously tunnel from our current vacuum to the lower minimum. The probability of this occurring in any given region of space in any given moment is astronomically small. But the universe is large, and time is long, and the probability that is very small, but not zero, will eventually produce an outcome. The Higgs field is not where it should be if our vacuum were absolutely stable. It is sitting in a temporary configuration, a configuration that has persisted for 13.8 billion years and will very likely persist for timescales that make the current age of the universe seem negligible. But temporary and stable are not synonyms, and the distinction between them, however irrelevant it is to any practical human concern, is a statement about the nature of the reality we inhabit. We do not live in the ground state, we live above it, and the ground, in the strict sense of the word, is somewhere below us, separated from where we stand by a barrier that quantum mechanics regards as a statistical inevitability rather than an absolute wall. The vacuum decay and the bubble that ends everything. The mechanism by which the universe could transition from its current vacuum state to a lower one has a name, and the name is straightforward: vacuum decay. The straightforwardness of the name is misleading. What it describes is not a physical process in the ordinary sense, a sequence of events unfolding over time in a way that could in principle be observed and traced. It is a quantum event, a causal and instantaneous at the scale of its initiation, with consequences that propagate outward at the maximum speed that physics permits. Here is how it works. At some point in space, a small region of the Higgs field undergoes a quantum fluctuation of sufficient magnitude to tunnel through the energy barrier, separating our current vacuum from the lower energy state. This event does not require a trigger. It does not require a special set of conditions. It does not need a high-energy particle collision or a specific density of matter. It is a purely probabilistic event, like radioactive decay, that can occur at any point in space at any time. The probability per unit volume, per unit time, is extraordinarily small, small enough that the expected waiting time for such an event in any region the size of the observable universe is many orders of magnitude longer than the current age of the universe. But it is not zero. When the tunneling event occurs, the small region of space that has transitioned to the new vacuum state is separated from the surrounding space by a thin wall, a boundary across which the value of the Higgs field changes discontinuously from the old vacuum value to the new one. This boundary is called the bubble wall. The new vacuum state, being at a lower energy, is thermodynamically preferred. The bubble expands, the bubble wall moves outward in all directions at the speed of light, converting everything it encounters from the old vacuum state to the new one. Inside the bubble, the laws of physics are different. The Higgs field takes a different value, which means every particle that acquires mass through the Higgs mechanism acquires a different mass. But different is not an adequate description of the actual situation. The new vacuum state is not simply our universe with slightly different constants. It is a configuration of physical law that was arrived at by minimizing the Higgs potential. And there is no reason to assume that this configuration permits the existence of atoms or nuclei or electrons in stable orbits or any of the other structures that chemistry and biology require. The new vacuum would be, by all reasonable expectations, hostile to every form of complexity that has ever existed, and it would arrive without warning. The bubble wall moves at the speed of light. The only way to learn of the bubble's existence before it reaches you is to receive a signal that preceded the wall, and no signal can travel faster than the wall itself. If a vacuum decay event occurred right now at a distance of 1 million light years from Earth, the first possible moment at which any signal from that event could reach Earth is 1 million years from now. And that is also the moment at which the bubble wall would arrive. Information and destruction travel at the same speed. Observation and annihilation are simultaneous. There is no defense, there is no preparation, there is no technology that could detect the bubble in time to respond, because responding faster than light is precisely what physics forbids. The transition from existing to not existing would occur at a boundary without any phenomenology preceding it. There is no version of this scenario in which you experience the approach. There is no flash of light, no warning signal, no moment of realization. The boundary is the end of the conditions under which experience is possible. This is the mechanism that CERN's data is making more, not less, credible. And understanding why requires understanding what the new measurements actually show and what they imply about the shape of the landscape we are navigating. The CERN's new data and the measurement that changed the question. Science does not usually advance through single dramatic revelations. It advances through the slow accumulation of precision, measurements that begin imprecise, narrow over time, and eventually converge on a value with enough accuracy to make theoretical calculations meaningful. The history of particle physics is largely a history of this process. A prediction made, an experiment designed, a measurement taken, a discrepancy noted, a theory adjusted, the cycle beginning again. The drama, when it occurs, is usually invisible to the public until after it has already happened. The measurement that has changed the question of vacuum stability is not a single experiment. It is a convergence of results from the Large Hadron Collider's Run 2 and Run 3 data collection periods, this spanning from 2015 to the present, during which CERN systematically improved the precision of measurements across a wide range of physical parameters. Among the most consequential of these measurements are the refined determinations of the Higgs boson mass and the top quark mass, both of which enter directly into the renormalization group equations that determine the fate of the Higgs self-coupling at high energies. The Higgs boson mass, as of the most recent combined CERN measurements, is 125.25 plus or minus 0.17 gigaelectron volts. This precision, better than 0.1%, is sufficient to place meaningful constraints on the shape of the Higgs potential at energies many orders of magnitude higher than those directly probed by the LHC. The top quark mass, measured at approximately 172.5 gigaelectron volts with an uncertainty of less than 1%, is equally important because the top quark's large coupling to the Higgs field makes it the dominant contributor to the quantum corrections that drive the Higgs self-coupling negative at high energies. When these values are entered into the renormalization group equations and evolved to high energy scales, the result is a calculation of the energy at which the Higgs self-coupling crosses zero and becomes negative. This energy scale, approximately 10 to the power of 10 to 11 gigaelectron volts, defines the onset of vacuum metastability. Below this scale, our vacuum appears stable. Above it, the potential slopes downward toward a deeper minimum. The question of which side we are on is determined by the precise values of the Higgs and top quark masses, and the current measurements place us squarely in the metastable regime. This is not a new conclusion. Physicists have suspected since the early 2000s that the measured Higgs mass places us near or within the metastable region of parameter space. What is new is the precision with which this conclusion can now be stated, and the degree to which CERN's Run 3 data has begun to close the windows of uncertainty through which an alternative interpretation might have escaped. Several proposed mechanisms for stabilizing the vacuum, including certain supersymmetric models and specific extensions of the standard model, predict new particles at energy scales that the LHC should have been able to detect by now. Those particles have not been found. Their absence is not proof that they do not exist, but it narrows the space of theories that could rescue us from metastability, and every search that comes up empty makes the metastable picture more difficult to dismiss. The question has changed. It is no longer whether the Higgs mass is consistent with a metastable vacuum. It is. The question is now whether the theoretical framework that predicts metastability is complete, and whether the mechanisms that might stabilize the vacuum exist at energies we cannot yet reach. And that is a question the data is not positioned to answer definitively, but is positioned for the first time to make genuinely urgent. The renormalization group and the shape of the abyss. There is a mathematical tool at the center of this analysis that deserves its own explanation, because without it, the significance of the Higgs mass measurement cannot be fully appreciated. The tool is called the renormalization group, and it describes one of the most counterintuitive features of quantum field theory: the fact that the apparent values of physical constants depend on the energy scale at which you measure them. This sounds wrong. Constants are supposed to be constant. The electron charge, the Higgs mass, the coupling between the top quark and the Higgs field. These are fundamental parameters of nature. They should not change with energy. In classical physics, they do not. But in quantum field theory, every measurement of a physical quantity is affected by the quantum fluctuations of the vacuum at the energy scale of the measurement. Different measurements performed at different energies probe different aspects of these fluctuations, and the effective value of any given coupling constant, as observed at a particular energy scale, depends on all the virtual particle interactions that occur at energies up to and including the measurement scale. The renormalization group equations describe how these effective values change as you move from one energy scale to another. They are equations of flow, describing how the coupling constants run as you turn up the energy dial. For some constants, the running is mild, a small change over many orders of magnitude in energy. For others, particularly those that couple strongly to heavy particles, the running can be dramatic. The Higgs self-coupling, which controls the shape of the Higgs potential and therefore the stability of the vacuum, runs significantly. At the low energies we can directly measure, it is positive, meaning the Higgs potential is bowl-shaped and the vacuum is locally stable. But as the energy increases, the coupling decreases. At an energy scale that current measurements place at approximately 10 to the power of 10 or 11 gigaelectron volts, the coupling passes through zero, and above that scale, it becomes negative. A negative Higgs self-coupling corresponds to a Higgs potential that, rather than rising on both sides of the minimum and confining the field to a bowl-shaped region, begins to fall away at large field values. The potential develops a second, deeper minimum at a much higher field value. Then this is the theoretical basis for vacuum metastability. The field is confined to the local minimum at our current vacuum expectation value by a barrier, but the global minimum of the potential lies far away at a much higher field value. The Higgs field is not at the bottom of its energy landscape. It is at a rest stop partway down. The precision of this picture depends entirely on the precision of the input parameters. Small changes in the Higgs mass or the top quark mass shift the energy scale at which the self-coupling turns negative, and they can, in principle, shift it below the Planck scale, where new physics is expected to dominate, and the standard model calculation becomes unreliable. If the turnover happens above the Planck scale, the standard model itself becomes invalid before the instability is reached, and new physics might save us. But the current measurements place the turnover squarely within the regime where the standard model is expected to be valid, below the Planck scale by several orders of magnitude. There is no calculational excuse left. The map of the abyss has been drawn with precision sufficient to take seriously. And what the map shows is that we are standing near the edge, the role of dark energy in the instability calculation. The connection between vacuum decay and dark energy is not coincidental. It is structural. They are two faces of the same underlying question. What is the energy of the vacuum, and is it stable? Dark energy, as represented by the cosmological constant, is the observational measure of the vacuum energy. It is what you get when you measure the effect that empty space has on the large-scale geometry and expansion of the universe. Its value is the energy density of the vacuum in its current configuration. It is a number, small but non-zero, that describes the state of the Higgs field and all the other quantum fields that contribute to the vacuum energy. And it is the number that would change if the vacuum decayed. If the Higgs field tunneled from its current minimum to the deeper minimum at higher field values, the vacuum energy of the new state would be different. The cosmological constant of the new vacuum would take a new value. Depending on the shape of the deeper minimum, this new value could be larger than our current value, which would produce an even faster expansion. Or it could be negative, which would produce something qualitatively different, a contraction. A universe with a negative cosmological constant does not expand forever. It collapses. The geometry of space-time curves in on itself, and the universe ends in a final singularity, the theoretical inverse of the Big Bang, sometimes called the Big Crunch. The value of the cosmological constant in the new vacuum is not something that current physics can calculate with confidence, because it depends on the shape of the potential at field values that lie far beyond our experimental reach. But what can be said is that our current cosmological constant, the dark energy we observe, is a precise measurement of the vacuum state we currently occupy. And every refinement of that measurement by cosmological surveys and by CERN's particle physics data is a more precise determination of where, exactly, we sit in the energy landscape. CERN's contribution to this determination is the precision measurement of the parameters that control the shape of the Higgs potential. The cosmological survey's contribution is the precision measurement of the dark energy density and its evolution over time. When these two lines of evidence are combined, they provide something that no single measurement could achieve. A picture of the vacuum from two different perspectives, one from the inside of particle physics, measuring the structure of the Higgs field, and one from the outside of cosmology, measuring the large-scale consequences of that structure. And the picture they jointly produce is consistent with a vacuum that is not at its lowest energy state, that has a cosmological constant produced by a temporary configuration of the Higgs field, and that may be evolving slowly toward a different configuration. The dark energy we observe is not necessarily permanent. It is a measurement of the current state. Whether that state is eternal or transitional is the question that both lines of evidence are beginning to bear upon. And the answer they are beginning to converge on is not the comfortable one. The landscape of possible universes. String theory is the most ambitious theoretical framework in modern physics. It attempts to describe all fundamental forces and all matter in terms of the vibrations of one-dimensional objects, strings, operating in a space-time of more than 4 dimensions. It has produced remarkable mathematical results, revealed deep connections between different areas of physics, and attracted a generation of the most talented theoretical physicists in the world. It has also, after 50 years of development, produced no confirmed experimental predictions. This is not a secret, and it is not the point here. The point is that string theory, in attempting to derive the laws of physics from first principles, discovered something unexpected about the structure of physical law. It discovered that there is not one consistent vacuum state for a universe described by string theory. There are many, not a few, not dozens, but a number so large it challenges the concept of a number as a finite thing. Approximately 10 to the power of 500 distinct vacuum states, each corresponding to a different compactification of the extra dimensions that string theory requires, each with its own value of the cosmological constant, its own particle masses, its own coupling constants, its own physical laws. This collection of possible vacua is called the string theory landscape. In the landscape, our universe occupies one point. The laws of physics we observe, the constants we measure, the forces we feel, are all specific to the vacuum state we happen to inhabit. Other vacuum states would have different laws, different constants, different forces. Most of them would be inhospitable to any form of complexity because the parameters governing nuclear physics, atomic structure, and chemistry would not fall in the ranges that permit stable atoms, molecules, or life. But some of them would be habitable, and in an eternally inflating universe, all of them may be realized, each in its own bubble of space-time, though expanding independently within a larger inflationary background. The landscape has a disturbing implication for the question of vacuum stability. If there are 10 to the power of 500 possible vacuum states arranged in a landscape of energies, then our universe did not necessarily nucleate in the lowest possible energy state. It nucleated in some state determined by the quantum fluctuations of the early inflationary epoch, and it may not be at the bottom. It may be a relatively high energy state that has persisted because the barriers separating it from lower states are high enough that quantum tunneling has not yet bridged them. Or it may be a relatively low energy state, close to the global minimum, with little room to fall further. Current measurements cannot distinguish between these possibilities. They can only tell us that we are not at the lowest accessible energy, and that there is, almost certainly, something lower than where we stand. In the landscape picture, vacuum decay is not a unique event. It is the norm. Universes nucleate, expand, and decay into lower vacua. which themselves expand and may eventually decay further. The process is fractal and eternal, a self-reproducing structure of bubble universes, each containing different laws of physics, each temporary in the absolute sense while appearing eternal from the inside. Our universe is one such bubble. It has been expanding for 13.8 billion years. It will very likely continue expanding for an incomprehensible duration. But the duration is not infinite. It has a statistical endpoint. And the landscape tells us that the endpoint is not hypothetical. It is the expected behavior of systems like the one we inhabit. What the cosmological constant problem actually means. Return for a moment to the number 10 to the power of 120. Sit with it, not as an abstract quantity, but as a statement about the relationship between two of the most successful theories in the history of science. Quantum field theory and general relativity both work. Each, within its domain, produces predictions of extraordinary precision. The standard model of particle physics describes the behavior of subatomic particles with an accuracy unmatched in any other field of human inquiry. General relativity describes the behavior of gravity and the large-scale structure of space-time with an accuracy that has survived every experimental test, including the recent detection of gravitational waves and the imaging of black holes. Both theories are real. Both work. When you combine them, you get a contradiction of 120 orders of magnitude. This is not a problem of incomplete data or experimental error. The cosmological constant problem is a conceptual problem, a fundamental incompatibility between the way quantum field theory treats the vacuum and the way general relativity treats the energy content of the universe. Quantum field theory says the vacuum is full of energy. General relativity says that energy curves space-time. The energy that quantum field theory predicts for the vacuum would produce a curvature of space-time so extreme that the universe would have collapsed or exploded in the first instant of its existence. It did neither. We are here. The universe exists in a form that permits the question to be asked, and this fact, the fact of our existence, is in some sense the only data point that we have for why the cosmological constant is not what it should be. Several approaches have been proposed to address this. The first is supersymmetry, a theoretical framework that postulates the existence of partner particles for every known particle, with the property that the vacuum energy contributions of the supersymmetric partners cancel those of the standard model particles, leaving a much smaller net result. This cancellation would be exact in an unbroken supersymmetric theory, producing a cosmological constant of exactly zero. In a theory where supersymmetry is broken at some energy scale, as it must be to be consistent with observation, since no supersymmetric partners have been found at accessible energies, the cancellation is incomplete, and the residual cosmological constant depends on the scale of supersymmetry breaking. For supersymmetry to explain the observed cosmological constant, the breaking scale would need to be extraordinarily precisely chosen, essentially replacing the original fine-tuning problem with a different one. The second approach is the anthropic principle, combined with the landscape. If there are an enormous number of possible vacuum states, each with a different cosmological constant, then observers can only exist in vacua where the cosmological constant is small enough to permit the formation of galaxies, stars, and planets. In vacua, with a large positive cosmological constant, the universe expands too rapidly for matter to clump into structures. In vacua, with a large negative cosmological constant, the universe collapses before structures form. The observed value of the cosmological constant is small enough to permit structure formation, but large enough to be measurable. On the anthropic view, this is not a coincidence. It is a selection effect. We observe the value we observe because only this range of values permits us to exist and observe. The anthropic argument is mathematically coherent. It is also philosophically unsatisfying to many physicists because it does not explain the cosmological constant in the traditional scientific sense. It does not derive the value from deeper principles. It explains why we would observe this value given the assumption of a vast landscape of possible values. But it does not tell us whether the landscape is real or what determines the probabilities of different vacua being realized. It is an explanation that in explaining one mystery introduces a larger one. CERN's measurements are relevant to all of these approaches. They narrow the space of viable supersymmetric models. They provide precision input to the renormalization group calculation of vacuum stability. They refine the measurement of the cosmological constant's value. And in doing so, they make the theoretical problem more constrained and in a meaningful sense, more urgent. The worst prediction in the history of science remains wrong by 120 orders of magnitude. But the precision with which we now know it is wrong has increased dramatically. And increased precision, in this case, has not brought us closer to an explanation. It has made the absence of an explanation harder to ignore. The speed of the bubble and why distance offers no safety. There is an instinct, when confronted with a threat that is large but distant, to take comfort in the distance. A hurricane forming in the Atlantic offers some time for preparation. A civilization-ending asteroid gives, if detected early enough, years or decades. Even cosmic events that occur on timescales beyond human comprehension, the death of the sun in 5 billion years, the heat death of the universe in 10 to the power of 100 years, are distant enough that the distance itself constitutes a practical protection. We are not required to act because we cannot act, and the knowledge of a distant catastrophe sits differently in the mind than the knowledge of an immediate one. Vacuum decay does not allow this distance to function as comfort. The reason is simple and follows directly from the structure of special relativity. When a vacuum decay event occurs, the bubble of new vacuum expands outward at the speed of light. This is not because the expansion is driven by any force that happens to propel it at that speed. It is because the speed of light is the maximum speed at which a causal influence can propagate through space. The transition from the old vacuum to the new vacuum is a physical change in the state of the Higgs field. That change propagates outward through space by influencing adjacent regions, and the maximum speed at which any influence can spread from one point to another is the speed of light. The bubble wall therefore moves at exactly the speed of light, not approximately, not just below, but exactly. The speed of light is also the speed at which information travels. It is the maximum speed at which any signal of any kind, light, radio wave, gravitational waves, any physical carrier of information can propagate. This means that the bubble wall and the first possible signal about the bubble's existence travel at the same speed. They arrive simultaneously. If a vacuum decay event occurred at a point 1 light year away from you, you would not be able to detect it until exactly 1 year after it occurred. And at the moment the detection would become possible, the bubble wall would also arrive. There is no interval between knowing and ending. The gap between information and consequence is zero. Distance, in the context of vacuum decay, does not provide warning time. It provides only ignorance time. Then, the period during which you do not know that something is approaching, and this period ends at the same moment the approach does. This is not a feature of vacuum decay that can be engineered around. It is not a technological limitation. It is a consequence of the structure of space-time itself, and the best physics we have says that structure will not change, regardless of how advanced any civilization becomes. You cannot move faster than the bubble. You cannot receive a signal before the bubble arrives. You cannot relocate to a safe distance, because no safe distance exists within the bubble's eventual reach. The only protection is for the event not to occur, and the event's probability of not occurring is not a certainty. It is a very high probability, high enough that no rational person should spend significant mental energy worrying about it in practical terms. But the distinction between a very high probability and a certainty is not merely semantic. It is the distinction between a universe that is absolutely stable and one that is not. And CERN's data, with increasing confidence, is pointing toward the latter. How long does the vacuum last? This is the question that provides the most direct confrontation between the disturbing implications of vacuum metastability and the practical reality of human existence. How long, given everything the data tells us, would we expect our vacuum to persist? The calculation of vacuum lifetime involves quantum tunneling rates, which depend on the height and width of the energy barrier separating our current vacuum from the lower one, as well as on the energy difference between the two states. These quantities are determined by the shape of the Higgs potential at large field values, which is in turn determined by the Higgs self-coupling as evolved by the renormalization group equations. The calculation is technically involved, but the result is not ambiguous in its order of magnitude. Current best estimates for the lifetime of our vacuum, based on the measured Higgs and top quark masses and standard assumptions about the behavior of the potential, range from approximately 10 to the power of 100 years to 10 to the power of 400 years. These numbers are so large that they require some context to appreciate. The current age of the universe is approximately 10 to the power of 10 years. The time until the Sun expands and engulfs the Earth is approximately 5 times 10 to the power of 9 years, trivially small on this scale. The time until the last stars burn out is approximately 10 to the power of 14 years. The time until protons decay, if they do, is at least 10 to the power of 34 years. All of these timescales, the entire future history of stars and matter, are compressed into a negligible fraction of the lower end of the vacuum lifetime estimate. By any measure that is meaningful on human or even cosmic timescales, the vacuum is stable. The probability of vacuum decay occurring during the lifetime of the Earth, or the Sun, or the galaxy, or even during the duration of the stelliferous era of the universe, when stars still burn, is so small as to be effectively zero. No one alive today, or any descendant of anyone alive today, or any civilization that might arise on any planet in the observable universe within the next trillion years, has any practical reason to be concerned about vacuum decay. The number is large enough to constitute functional permanence for every purpose that matters. But the lifetime estimate carries with it assumptions about the absence of new physics between our current energy scale and the Planck scale. If the physical theory is correct and no new stabilizing mechanism exists, then the lifetime is finite. And the finite lifetime, however large, is not the same as an infinite one. The distinction is not merely philosophical. A universe with a finite vacuum lifetime is categorically different from one with an infinite vacuum lifetime. In the first case, everything that exists is temporary in the most absolute sense. In the second case, the conditions for existence are permanent. CERN's data, by ruling out several proposed stabilizing mechanisms and tightening the constraints on the Higgs potential, has moved the balance of evidence toward the first category. The vacuum will very probably last far longer than any mind can encompass. But very probably is not certainly. And the question of whether we live in a truly permanent universe or a very long-lived temporary one is not a matter of practical concern. It is a matter of what is actually true. Science has always pursued that distinction, even when the truth offers no comfort. The anthropic shadow over the evidence. One of the most important and most frequently misunderstood arguments in contemporary cosmology goes like this. We observe that the vacuum has not decayed. We have been observing the universe for approximately 100 years with modern instruments, and for thousands of years before that with the naked eye. In all of that time, we have seen no evidence of an expanding bubble of new vacuum, no region of the sky where the laws of physics appear to have changed, no dimming of distant galaxies, consistent with the passage of a bubble wall. This absence of observation might seem like evidence that vacuum decay is either impossible or extremely improbable, a comforting indication that the universe is more stable than the worst-case calculations suggest. This reasoning is flawed. The flaw has a name: the anthropic shadow. The anthropic shadow refers to the way that the requirement for observers to exist in order to make observations systematically biases the observations we can make. In the context of vacuum decay, the argument works as follows. Any observer, by definition, exists in a region of space where the vacuum has not yet decayed. This is not a fact about vacuum stability. It is a tautology about observation. An observer whose vacuum has decayed is no longer an observer, and therefore contributes no data to our understanding. The set of all possible observations is by construction restricted to observations made in regions where the vacuum is intact. The absence of observed vacuum decay is therefore entirely consistent with a universe in which vacuum decay occurs regularly in other regions. We cannot see those regions because observers in those regions no longer exist. This is a subtler version of a more familiar bias. If you were to survey every person alive today, about whether they have ever been in a fatal car accident, you would find that none of them have been, because none of the people who died in fatal car accidents are available to answer your survey. The survey result, 0 deaths among respondents, tells you nothing about the frequency of fatal car accidents. It tells you only about the survivorship of the people taking the survey. Applied to vacuum stability, this means that the observation that our vacuum has survived for 13.8 billion years cannot be taken as strong evidence that vacuum decay is rare or impossible. It is evidence only that our vacuum has survived long enough for observers to evolve and make observations. If vacuum decay events are common in the multiverse, occurring regularly in regions that were briefly suitable for life, we would still expect to find ourselves in a region that has not yet decayed, because there is no other kind of region in which we could be asking the question. The anthropic shadow does not prove that vacuum decay is common or imminent. It does not change the calculated probability of decay in any given region. What it does is remove one of the most intuitive arguments for complacency, the argument that everything has been fine so far. Everything being fine so far is precisely what we would expect to observe, regardless of the overall decay rate, and therefore tells us essentially nothing about that rate. The one piece of evidence that might have made us feel safer turns out to be unavailable. The silence of an intact universe around us is not a reassurance, it is a selection effect. Dark energy is changing, and CERN can measure it. For 25 years, following the discovery of dark energy in 1998, the simplest and most widely adopted model was the cosmological constant model, in which dark energy is a fixed property of space, a constant energy density that does not vary with time or location. In this model, as the universe expands and matter and radiation thin out, dark energy comes to dominate, driving the expansion at an ever-increasing rate. The model is consistent with observation. It is elegant in the sense that it requires only a single parameter, the value of the cosmological constant. It has been the baseline assumption of cosmology for a generation, but it has always faced a theoretical challenge. If dark energy is a cosmological constant, a fixed property of the vacuum, then its value must be explained. And as we have discussed, the value it has is not the value that any known theoretical framework predicts. The cosmological constant model sidesteps this problem rather than solving it. It says, the vacuum energy has this specific value. The question of why it has this value and not another is left unanswered. An alternative class of models proposes that dark energy is not a fixed constant, but a dynamic field, a scalar field that permeates all of space and evolves over time. This field, called quintessence, would have an energy density that changes as the universe evolves, and its equation of state, the ratio of its pressure to its energy density, would differ slightly from the value of -1 that a true cosmological constant produces. A cosmological constant has an equation of state parameter, conventionally called W, of exactly -1. A dynamic dark energy field would have a W that departs from -1, either slightly above or slightly below, and might also vary with time. The distinction between a cosmological constant and a dynamic dark energy field is not merely academic. It has direct physical consequences. A dynamic dark energy would imply that the vacuum energy is not a static property of space, but an evolving process, a field rolling across its potential energy landscape in the same way that the Higgs field sits at its current minimum, and a field that is rolling is a field that is moving. It is heading somewhere. The question of where it is heading and what the endpoint of its evolution is the question that connects dynamic dark energy directly to the vacuum decay discussion. If dark energy is quintessence, a rolling scalar field, then the current vacuum energy is not the final state of the system. It is a snapshot of a process in motion. The field is evolving towards some lower energy configuration, just as the Higgs field may eventually tunnel to its own lower configuration. The difference is in the mechanism. The Higgs field would make its transition abruptly through quantum tunneling, while quintessence would evolve slowly through classical field dynamics. But both processes converge on the same fundamental picture. The vacuum is not permanent. Its properties are changing, though on timescales that may be far longer than the current age of the universe, but changing nonetheless. CERN's measurements contribute to this picture by providing precise constraints on the parameters that determine how the Higgs field and potentially quintessence evolve. The combination of particle physics data from CERN and cosmological data from large surveys is for the first time beginning to probe the dynamics of the vacuum from both ends. And the evidence for a vacuum that is evolving rather than static is accumulating in a way that is difficult to attribute entirely to systematic error. The DESI survey and the data that should not exist. In April 2024, the Dark Energy Spectroscopic Instrument, DC, released results from its first year of observations. DESI is an instrument mounted on the 4-meter Mayall telescope at Kitt Peak National Observatory in Arizona, equipped with 5,000 robotic optical fibers that can simultaneously measure the spectra of 5,000 galaxies, allowing it to map the large-scale structure of the universe with unprecedented speed and precision. In its first year of operation, it measured the spectra of approximately 6 million galaxies and quasars spanning cosmic distances that correspond to looking back over 11 billion years of cosmic history. The specific measurement DESI was designed to make is called the Baryon Acoustic Oscillation, BAO. Baryon acoustic oscillations are patterns imprinted in the distribution of matter across the universe, arising from sound waves that propagated through the hot plasma of the early universe before it cooled and recombined. These patterns have a characteristic scale, approximately 500 million light years, that serves as a standard ruler. By measuring how the scale appears to change with distance, observers can trace the expansion history of the universe, and from it, the behavior of dark energy over time. What DESI found when it compared its BAO measurements across different redshift bins spanning different periods of cosmic history was a deviation from the predictions of the simplest cosmological constant model. The deviation was not enormous. It was at the level of approximately 2 to 3 standard deviations in specific measurements, a level of statistical significance that is suggestive but not conclusive. But the direction of the deviation was consistent across multiple redshift bins and consistent with the dark energy that was evolving. There's specifically an equation of state parameter that departed from -1 in a way that suggested dark energy was weaker in the early universe and growing stronger over time. This result, if confirmed by future data, would rule out the cosmological constant as the correct description of dark energy. It would require a dynamic dark energy model, quintessence, or something like it, in which the vacuum energy is not a fixed property but an evolving field. And an evolving field, as discussed, is a field heading somewhere. The question of where it is heading is not answered by the DESI data. The data shows a direction of evolution, not a destination. But the direction, combined with the theoretical picture suggested by CERN's Higgs potential calculations, paints a coherent and uncomfortable portrait of a vacuum in slow transition. The DZ team was careful in presenting these results. They noted the statistical significance, acknowledged the possibility of systematic errors, and called for confirmation from future data. They were not claiming a discovery. They were reporting a tension, a place where the data and the simplest model are not in agreement. But tensions in science are the precursors of discoveries. They are the places where the map and the territory begin to diverge, and where the map eventually must be redrawn. The data that should not exist, if the cosmological constant is truly constant, now exists. It is preliminary. It is contested. It may be explained by systematic errors in the measurements, but it is consistent with everything else the evidence is saying. And in science, consistency across independent lines of evidence is the currency of credibility. The false vacuum and the illusion of ground. The phrase false vacuum appears frequently in discussions of vacuum stability, and it deserves careful attention because the word false is doing precise work here. It does not mean imaginary or illusory in the philosophical sense. It means locally stable, but not globally stable. A false vacuum is a configuration of a physical field that sits at a local minimum of its potential energy, a valley, but not the deepest valley available. It is false in the sense of being a wrong answer, a temporary solution that the system has settled into, not because it is the lowest energy option, but because the barriers separating it from lower options are high enough to make transition rare. Our vacuum, if the Higgs metastability calculation is correct, is a false vacuum. Every point in space, everywhere in the observable universe, is sitting in the same local minimum of the Higgs potential. The laws of physics we observe, the masses of the particles, the strengths of the forces, the very possibility of atoms and molecules and chemistry and biology, all of these are properties specific to this local minimum. They are not universal features of physical law. They are contingent features of the particular vacuum state we happen to inhabit. This contingency is philosophically significant in a way that takes a moment to absorb. When you look at the periodic table and observe the structure of atomic shells, when you observe the way chemical bonds form and molecules assemble, when you consider the extraordinary coincidences of physical constants that permit carbon chemistry and therefore life, you might be tempted to conclude that these features of reality are in some sense necessary, that they follow from some deep principle that could not be otherwise. The false vacuum picture says no. These features follow from the specific vacuum state we happen to occupy. In a different vacuum state, with a different value of the Higgs field, the masses of particles would be different. The strengths of forces would be different. Atoms, as we know them, might not be possible, and life as we know it would have no substrate on which to exist. The vacuum is not the foundation of physical law. It is one possible instance of physical law. The laws we observe are the laws of this vacuum. Other vacua have their own laws. And if the vacuum transitions, the laws change. Not in the way that a new scientific theory revises our description of existing phenomena. The laws change in the way that the rules of a game change when the game ends and a different game begins. The old rules do not continue to apply in a modified form. They simply stop being the rules. The false vacuum is the illusion that we are standing on solid ground, because the ground has not moved recently. It is the confusion of local stability with absolute permanence. It is the conclusion that because the floor has held for 13.8 billion years, it will hold forever. The physics says that this conclusion does not follow. The floor is real. The stability is real. The 13.8 billion years are real. But none of that makes the floor permanent. It makes it old. Old and permanent are not the same. And the difference between them is the difference between a universe that is truly stable and one that is merely waiting. What CERN cannot tell us. It is important, when discussing what CERN's measurements imply, to be equally clear about what they do not and cannot imply. The Large Hadron Collider is the most powerful particle accelerator ever built. Its collision energies of up to 13.6 tera-electron-volts are the highest ever achieved in a laboratory setting. Its detectors are marvels of engineering, capable of identifying particles with masses and lifetimes that were theoretical predictions only decades ago. And yet, by the standards of the energy scales relevant to vacuum stability, the LHC is a relatively low energy instrument. The instability of the Higgs potential, as currently calculated, occurs at energy scales of approximately 10 to the power of 10 or 11 gigaelectron-volts. The LHC operates at energies 4 orders of magnitude below this scale. The Planck scale, where quantum gravity becomes relevant and the standard model certainly breaks down, is another 8 or 9 orders of magnitude above the instability scale. This means that the LHC's measurements, however precise, are being extrapolated across enormous ranges of energy using the renormalization group equations on the assumption that the standard model remains the correct description of physics all the way to the instability scale. This assumption may be wrong. There may be new physics beyond the standard model that becomes relevant at energies between the LHC's reach and the instability scale. This new physics could, in principle, change the trajectory of the Higgs self-coupling in ways that prevent it from turning negative. Supersymmetric particles at an intermediate energy scale would do this. A new scalar field that mixes with the Higgs could do this. Modifications to gravity at intermediate scales could do this. The LHC has not found any of this, but the LHC has not ruled them out at all energy scales above its reach. The absence of new physics in the explored range does not guarantee its absence everywhere. Equally, there may be physics at or above the Planck scale that fundamentally changes the calculation. Quantum gravity, whatever form it eventually takes, will modify the behavior of fields at Planck energies in ways that the standard model cannot predict. If the Higgs coupling becomes negative below the Planck scale, it enters a regime where quantum gravity effects are significant, and these effects might stabilize the potential in ways that classical field theory cannot see. This is speculative, but it is not unreasonable. The history of physics is full of cases where a crisis in one theory was resolved by the discovery that the crisis occurred in a regime where the theory was not valid. What CERN can tell us is where the standard model, taken at face value, predicts the vacuum to be. It can tell us that the measured parameters are consistent with a metastable vacuum, that several proposed stabilizing mechanisms have not been found, and that the evidence for dynamic dark energy is growing. What it cannot tell us is whether the standard model is the complete description of physics between the electroweak scale and the instability scale. And this limitation is not an engineering problem that a more powerful accelerator would solve. A collider energetic enough to directly probe the instability scale would need to be of planetary or stellar dimensions, well beyond any technology conceivable to current physics. The answer to whether physics beyond the standard model stabilizes our vacuum is not, on any realistic timescale, going to come from a particle accelerator. It may come from theoretical insight. It may come from indirect observations. It may not come at all. The edge of what CERN can tell us is precisely where the most important question lives, and this is not a coincidence. The most important questions in science consistently position themselves just beyond the reach of available tools. This is the nature of the frontier. But it also means that the unsettling picture painted by current data may be the most complete picture we will have for a very long time. And the unsettling picture says that we are not certain we are stable. We are only certain that we have not yet decayed. The multiverse as a map of what has already happened. If the landscape of string theory is real, and if eternal inflation is real, then the multiverse is not a prediction about the future. It is a description of what is already happening. Right now, in the larger inflationary background from which our universe nucleated, new bubble universes are forming at an incomprehensible rate. Each one is a quantum fluctuation of the inflaton field, a local region where inflation ends and the pocket universe begins, with its own value of the cosmological constant, its own particle masses, and its own physical laws. Most of these universes are hostile to any form of complexity. Their physical laws do not permit the formation of stable atoms, or they expand too fast for matter to clump, or they are too short-lived to allow any process of sufficient complexity to evolve. A tiny fraction fall within the range of parameters that permit structure, chemistry, and eventually observers. In this picture, our universe is not special except in the sense that it is among the small fraction that permitted observers. It is one node in an infinite network of nucleation events, a single realized vacuum among an uncountable number of possible ones. The other nodes do not know of our existence. We do not know of theirs. The boundaries of our bubble universe mark the limit of causal contact. Beyond them, the inflating background continues, then other bubbles form, and the landscape of physical law is sampled across its full range. Some of those other bubbles may have already decayed. They nucleated in a metastable vacuum, as we did, persisted for some duration, and then underwent a vacuum decay event, transitioning to a lower energy state. The transition produced a new bubble of lower energy vacuum, expanding within the original bubble at the speed of light. The original bubble's laws of physics were replaced by the new vacuum's laws. Whatever complexity had developed within the original bubble, whatever structures or processes had taken advantage of the billions of years of stability, ceased to be possible at the moment the bubble wall arrived. This is not a prediction about our future. It is a description of what the landscape, if real, says is the general case: metastable vacua decay. The ones that last long enough to produce observers who naturally believe themselves to be in a stable universe because they have only ever experienced stability. But the belief is not the same as the fact. The appearance of stability is what observers in metastable vacua always observe, right up to the moment they don't. The multiverse picture is sometimes invoked as a solution to the cosmological constant problem, explaining why we observe a small value through the anthropic selection of habitable vacua. But it also, unavoidably, maps out a cosmos in which vacuum decay is not exceptional but expected, not a theoretical extreme case, but the generic endpoint of the kind of universe we inhabit. If we are in a metastable vacuum, as the data suggests, then we are exactly the kind of universe that the multiverse picture says eventually decays, and the map of what has already happened to other vacua in the landscape is a map of what will eventually happen to ours. The silence of the observable universe. The observable universe is vast beyond easy comprehension. Its diameter is approximately 93 billion light-years. It contains an estimated 2 trillion galaxies. Each galaxy contains, on average, hundreds of billions of stars. The total number of stars in the observable universe is approximately 10 to the power of 24, a number that exceeds the number of grains of sand on every beach on Earth by many orders of magnitude. Across this volume, over a period of 13.8 billion years, an enormous number of physical events have occurred. Nuclear reactions, stellar explosions, black hole mergers, galaxy collisions, the formation and dissolution of planetary systems, the possible emergence and extinction of civilizations. The universe is not quiet. It is extraordinarily active. And yet, in all of this, we have detected no sign of an advancing vacuum decay boundary. No region of the sky where the apparent laws of physics have changed. No anomalous absence of expected radiation from regions where a bubble wall might have passed. No edge in the distribution of galaxies that could be interpreted as the boundary of a new vacuum bubble. The silence across the entire observable universe, across the entire history of our observations, is complete. This silence is not surprising, and it is not reassuring. It is not surprising because the probability of a vacuum decay event occurring in the observable universe during the current cosmic epoch is, by the best available calculation, extraordinarily small. If the vacuum lifetime is 10 to the power of 100 years or more, the probability of a decay event in the entire observable universe during the 13.8 billion years we have been watching is negligible. We should not expect to see a decay event. The absence of one tells us almost nothing about the decay rate. It is not reassuring because, as discussed in the context of the anthropic shadow, we could not observe ourselves existing in a universe that had already undergone vacuum decay. The silence is a selection effect. It is guaranteed by the fact that observers require an intact vacuum not by any intrinsic stability of the vacuum itself. But there is a third reason the silence is worth dwelling on. Beyond its statistical expectedness and its anthropic inevitability, it is a reminder of the scale of the uncertainty we are operating within. We can see 93 billion light years in every direction. We can measure the properties of galaxies billions of light years away. We can detect gravitational waves from black hole mergers across cosmic distances. We are not observationally limited in any ordinary sense. And yet, the question of whether our vacuum is stable or metastable cannot be resolved by looking outward. The answer is not in the sky, it is in the mathematics of a potential energy landscape at field values that no observation, however precise, can directly sample. The silence of the observable universe, in the end, is not evidence for anything. It is a reminder that the most important question about the nature of the reality we inhabit is one that observation cannot definitively answer, and that the mathematics, when followed to its conclusions, produces a picture that the silence cannot refute. What physics looks like at the edge of the transition. It is natural to ask what the transition itself would look like, not from the outside, which we have already established would be unobservable in practice, but from the perspective of any physical system caught within the expanding bubble. The question is partly philosophical, since there would be no observer in any meaningful sense within the bubble to report its experience. But the physics of the transition can be analyzed, and the analysis reveals something that is more disturbing for being so clinical. The bubble wall is not a region of space where the laws of physics are suspended. It is a region where the value of the Higgs field changes from the old vacuum expectation value to the new one. This change occurs across a thickness that is set by the dynamics of the transition, typically extraordinarily thin by macroscopic standards, perhaps as thin as the Planck length in the most abrupt cases, though the precise width depends on the shape of the potential barrier. Within this thin wall, the Higgs field is in an intermediate configuration, and the properties of matter in this intermediate zone are not those of either the old or new vacuum. Outside the bubble, ahead of the wall, physical law is as we know it. Inside the bubble, behind the wall, physical law has taken on whatever properties correspond to the new vacuum. The new vacuum's Higgs field value is different, perhaps enormously different, from our current vacuum's value. This means every particle that acquires mass through the Higgs mechanism acquires a different mass. The electron, the quarks, the W and Z bosons, all of them would have different masses in the new vacuum. The strengths of the fundamental forces would be different because the coupling constants are related to the Higgs field value. The ratio between the electromagnetic and gravitational forces, which must fall within a precise range for stable atoms to form, would almost certainly be different. The probability that the new vacuum's parameters fall within the range necessary for stable atomic nuclei is essentially zero, not because there is any reason for the new minimum to have hostile parameters, but because the space of possible parameter combinations is vast and the set that permits stable atomic structure is extremely small within it. The new vacuum, with overwhelming probability, would be one in which protons and neutrons cannot form stable nuclei, in which electrons cannot maintain stable orbits, in which the chemistry that underlies all biological processes has no basis. This does not mean the new vacuum would be empty. It would still contain energy. It would still contain quantum fields. It might contain particles of some kind, configurations of the fundamental fields appropriate to the new vacuum's laws. But these configurations would not be atoms, molecules, proteins, neurons, or any of the structures that constitute matter as we know it. The universe inside the bubble would be physically real. It would be governed by consistent mathematical laws. It would simply be a universe in which nothing familiar is possible. And the transition from our universe to that universe would occur at the boundary instantaneously for every physical system that the boundary reached. There is no gradual deterioration, no slow change, no period of adaptation. The bubble wall is a step function in the value of the Higgs field. On one side, the laws of our vacuum. On the other side, the laws of the new vacuum. The transition is not a process experienced by the systems caught within it. It is a boundary they cross without crossing it, a change that eliminates the conditions for experience at the moment of its occurrence. What CERN's results actually confirmed, it is worth taking stock at this point in the analysis of what the evidence actually shows and what it does not show. The implications of the data are disturbing, and disturbing implications are sometimes mistaken for disturbing facts. The facts, as currently established, are more specific and more carefully qualified than the implications suggest, and it is important to represent them accurately. What CERN's measurements have confirmed, with the precision achievable by Run 2 and Run 3 of the Large Hadron Collider, is the following. The Higgs boson has a mass of 125.25 plus or minus 0.17 gigaelectronvolts. This measurement is confirmed by multiple independent analyses and is not in significant dispute. The top quark has a mass of approximately 172.5 gigaelectronvolts, with an uncertainty of less than 1% across multiple measurement channels. These two masses, discussed when entered into the renormalization group equations of the Standard Model, produce a Higgs self-coupling that becomes negative at an energy scale of approximately 10 to the power of 10 or 11 gigaelectronvolts. A negative self-coupling at this energy scale is consistent with, but does not conclusively prove, a metastable vacuum. It is consistent with metastability because it implies that the Higgs potential has a second minimum at very high field values, separated from our current minimum by an energy barrier. It does not conclusively prove metastability because the calculation depends on the Standard Model remaining valid up to the instability scale, and new physics at intermediate energies could change the result. Several proposed mechanisms that would stabilize the vacuum, including light supersymmetric particles and certain extra-dimensional models, have not been found at the energies the LHC has explored, making them less plausible but not impossible. What the DESI survey has provided, independently, is evidence for a dark energy that may not be constant, an equation of state parameter that departs from -1 at a level of 2 to 3 standard deviations in some redshift bins. This result is preliminary and requires confirmation from future data. It is consistent with the dynamic dark energy model, which would imply that the vacuum energy is evolving, but it does not prove this. what the combination of these results suggests, when taken together with the theoretical framework of the Higgs potential and the landscape, is a picture in which the vacuum is metastable, the dark energy is dynamic, and the universe is in a slow transition toward a different configuration. This picture is consistent with the available evidence. It is not required by it. An alternative interpretation, in which new physics stabilizes the vacuum and the DZ anomaly is a systematic error, remains possible. Science does not yet have the tools to definitively distinguish between these interpretations, but the direction of the evidence and the rate at which remaining uncertainties are being narrowed is meaningful. Each new precision measurement that is consistent with the metastable picture and inconsistent with proposed stabilizing mechanisms represents an accumulation of Bayesian evidence that is difficult to dismiss. The picture is not proven, but it is increasingly difficult to argue against. The question that has no comfortable answer. You are back where you started. A room, a chair, a floor that has not moved, walls that hold their shape. Everything around you is exactly as it was when this began. The light behaves the same way. The air does not change. Your body continues its processes without interruption. Nothing in your direct experience has shifted, but the information you now carry is different from the information you had before. You now know that the space you occupy has an energy value. That energy value has been measured with the most precise instruments humanity has ever built, and the measurement places it not at the lowest possible state of the system it inhabits, but at a local minimum, separated from a deeper minimum by a barrier that quantum mechanics does not treat as permanent. You know that the rate at which dark energy drives the expansion of the universe may be evolving, not constant, suggesting that the vacuum energy itself is a process rather than a property. You know that the mechanisms physicists had hoped might stabilize this configuration have not appeared at the energies where they were expected. You know that the anthropic shadow removes the most intuitive source of comfort, the observation that everything has been fine so far, because that observation is guaranteed regardless of the actual decay rate. And you know that if the transition ever came, it would come without warning, at the speed of light, replacing the laws of physics that permit your existence with laws that do not, in a process that would eliminate the conditions for experience at the moment of its occurrence. This knowledge does not require you to do anything. It does not change your plans for tomorrow or next year or the rest of your life. The vacuum will almost certainly outlast every civilization that will ever exist on any planet in the observable universe. The timescales involved are so vast as to constitute a practical infinity for every purpose except the strictly philosophical one. The question of what is actually true about the permanence of our reality does not bear on any decision any person will ever make, except that it does bear on something. It bears on the honest assessment of what we are and where we are. It bears on the question of whether the universe is a stage that was built to last, or a configuration that happens to have persisted long enough for us to ask about it. Science has always taken seriously the distinction between what appears to be true and what is actually true. The apparent stability of the vacuum is real. The concern about its actual stability is also real, and it comes not from philosophical anxiety, but from the most precise measurements ever taken of the most fundamental parameters in physics. What does it mean to live in a universe that may be temporary in the most absolute sense, not temporary like a civilization which leaves ruins, not temporary like a species which leaves descendants, temporary in the sense that the conditions which make the concept of you possible might not be permanent features of reality, but contingent properties of a specific vacuum state that has persisted for 13.8 billion years and will very probably persist for an incomprehensible duration beyond that, but which the mathematics says is not the final word. CERN has not solved the dark energy mystery. It has sharpened it. It has narrowed the range of possible answers and confirmed, with increasing precision, that the most uncomfortable of those answers is consistent with everything we can measure. The mystery remains. The ground remains. The room remains. But the ground is not what it appeared to be before you started asking questions about it. It never was. You have followed this question as far down as current physics allows. You have traced the evidence from the motion of distant galaxies to the curvature of a potential energy landscape that no instrument can directly observe. You have watched the most successful predictive framework in the history of science produce its most spectacular failure, and you have seen the measurements narrow the space of possible explanations until the uncomfortable one is the last one standing. The vacuum we inhabit is, by the best available evidence, not the ground state of reality. It is a local minimum, a temporary configuration, a rest stop in a landscape of possibilities that extends far below where we stand. The energy of the dark that fills space, the dark energy that is pulling the universe apart, is a measurement of the current vacuum state, and that state appears to be evolving. The barrier separating us from the lower state is high. The lifetime of our vacuum is immense, but neither the height of the barrier nor the immensity of the lifetime changes what they are, properties of a system that is temporary rather than permanent. What does this mean for how you understand the reality you inhabit? The physics does not say. It is not in the business of meaning. It is in the business of accurate description. And the accurate description is this: you are a temporary arrangement of matter that is possible only within the specific laws of a specific vacuum, sitting in a configuration that the mathematics of quantum field theory does not protect against change, in a universe that has been expanding for 13.8 billion years under the influence of an energy whose origin remains unexplained, whose constancy is now in question, and whose ultimate fate is not determined. This is not a reason for despair. It is not a reason for anything in particular. The knowledge that the vacuum is metastable does not make the air less real, the people around you less present, the things that matter to you less worth caring about. The implications are cosmological, the life is yours, but the question remains exactly where CERN's data left it. Not answered, not unanswerable, perhaps, but not yet answered. What is the vacuum? What keeps it where it is? What would move it? And how long, in the strictest possible sense of the word permanent, does forever last? The room is still there. The floor has not moved. The universe continues its expansion, carrying everything within it outward at an accelerating rate into a future that the data says will last for a very long time, but that the same data says is not infinite. That distinction is small. That distinction is everything